Okay, our next application relates to work. Recall that work is force times distance, so the amount of force exerted times the distance. Your typical unit for force is the Newton, which is a kilogram meter per second squared, or a capital N for Newton. And then a joule is just taking that and multiplying it by the distance you've gone. So the unit of work is the joule, which is a kilogram meter squared per second squared, or just a capital J. Those are your metric units. And there are similar work units. There are similar units in the English system. There you're dealing with pounds and foot-pounds. So the idea is, if we take an object and we're pushing it along some linear path, some distance, say from a point A to a point B. So we're taking some object and we're pushing it along that distance. Okay, and we want to compute the amount of work that's done in doing that. So we know the force. Now the force need not be constant. The force we're exerting along this need not be constant. Maybe we're pushing a little harder to start off, and then we let off a little bit, and maybe our force functions like this, and we give it a little bit bigger of a shove. We're not always exerting the same force as we're going from A to B. Right? Our force can be variable. It doesn't have to just be a constant force. Okay? So there's some function that tells us the amount of force we're exerting on the object at any one time. Okay? So we want to count the work that we're doing if we're doing a variable amount of force, not always the same. So once again, we would subdivide our interval, pick some point in the interval. Now I did a star point last time, but it really doesn't matter what point we pick. So I'm just going to estimate the force on that interval, across that interval, as f of x sub I. So that my work for that interval would just be the force that I exerted over that distance. So f of x sub I and down to x sub I, so that my work just becomes the integral from A to B of the force function with respect to x. Okay, so that is the idea of how we're going to do work. Now, we're specifically going to look at work in terms of working with springs. So maybe you've done a little bit in like a physics class with springs. And so that's what we're going to focus our attention on, is just springs. And so to do that, we need a result from physics known as Hooke's law. Known as Hooke's law. Maybe you've done something like this where you've been working with springs and you stretch at a certain length. See, what force are you exerting, because you're using a counter to see the force that you're pulling on it, or rather the force that the spring is pulling back against you on, right? And then you've stretched it to different lengths and looked at that, and maybe you've noticed this thing here, that the force, this result called Hooke's law, force required to keep a spring compressed or stretched from equilibrium, right, its balanced state, is f of x equals kx, where k is the spring constant. K is the spring constant. All right, so in other words, the force is proportional to how far you're stretching or compressing the spring. Is proportional to how far you're stretching or compressing the spring. So let's see an example here of using Hooke's law now, along with what we've just learned. We have the force. The force to stretch it 1 inch is different than the force to stretch it 2 inches. All right, so it's variable force depending on how far you've stretched it. Right, how far you're stretching it. That's going to determine the amount of force you're exerting in doing that. So, in our example, let's say that we know first of all that the force required to stretch a spring is 0.2 meters from equilibrium is 150 newtons. All right, so the first thing we want to do here is we want to find K. So we know that the force required to stretch it 0.2 meters is 150 newtons. That would be equal to Kx, but x here is 0.2. So that would be equal to 0.2 K. And so we can go ahead and use that to solve for K. So we do that, divide by the 0.2, and we know that for this particular spring, that the constant K is 750. And so our function, our work function, our force function is 750x. So now we ask the question, some questions about this. Now that we have our force function, right? So we know if we stretch it a whole 1 meter, that's going to take 750 newtons to do that. 2 meters would take 1,500 newtons of force. So now we ask some questions here about work. How much work is done if we compress a spring or not a spring, but rather the spring, the one we're working with. 0.3 meters from equilibrium. Okay. Now, of course, this is all assuming that these things can be done to our spring, right? mathematically, a mathematical spring, we can do this too. We can stretch it out and we don't have to worry about breaking the spring, or we can crush it as much and it'll always return back to its state. With actual springs, you do have to be a little more careful that you're not going past their breaking point. But here we're talking about a mathematical spring, so it works well. So what we're doing is we're taking it from its standard state and we're making it 0.3 meters smaller, right? We're taking the tip and pushing it back 0.3 meters. So in other words, we're actually starting at 0 and stretching it backwards or pushing it backwards to make it smaller. So our limits of integration here will actually be between 0 and negative 0.3. Then the result is that the work is the integral of your force function, 750x dx. So we work that out. So we integrate, add 1 to the exponent, makes it x squared. So 375x squared, evaluate it between 0 and negative 0.3. Okay, and go ahead and plug in your negative 0.3, and we'll get 33.75 joules of work are done when we do that. Okay. All right, so that is working with springs. And again, we could do it from any length. I did it here just from equilibrium, but if you already had the spring, compressed, tenth of an inch or tenth of a meter, then you could figure out the work to go the last 0.2 meters. So you could do it from negative 0.1 to negative 0.3. Or the same thing on stretching it. If you already had it stretched out half a meter, then you could stretch it from that point to a meter, right? And talk about how much work was done just in that latter part of it. Okay? All right.